full screen here. All right, so as I hopefully will write down in a few minutes, this is a deeper dive into getting some practice with graphing exponentials and exponential growth, exponential decay, their inverses, and e to the x and ln of x. It might take a little while, but get some practice in and understanding how to graph those algorithms quickly really boils down to understanding differentials, differences. Okay, so here's a typical exponential function. I've got a doubling function, and the differentials are here and here. Well, part of the graph is here, right? So y equals 7, exponential growth above a y value of 7. And the first initial jump is 8, and the next one is 16. That happens when I make the argument 0 and 1. So 2 to the 0 is 1. 1 times 8 is 8, plus 7 is 15. That's 8 units above 7. And 2 to the 1 is 2, times 8 is 16, plus 7, that's 16 above 7. 16 above 7 takes me to 23. And 8 above 7 takes me to 15. You can make that happen every single time by making this 0, which in this case is the year 2005. Oops, put it on the wrong one. 2005. And then 20 years later, 2025, we have a new amount whose differential is twice the initial jump. All right, so we have y equals 7. We have a jump of 8 and a jump of 16. Now the inverse of functions is switching the x's and the y's. So I hope you're looking at exponential growth as I'm looking at it. And then if I switch the x's and the y's, then, no, I didn't do it right. So here's your exponential growth, and switching the x's and the y's is going to look like that. Yep, got it right this time. Okay, so what is the inverse of a horizontal line, a vertical line, which is an x equals? What is the inverse of a vertical 8? A horizontal 8. What is the inverse of a vertical 16? A horizontal 16. Okay, barely saw that. All right, so get the camera facing the other way a little bit. And okay, so I'm suggesting it looks like that. I'm suggesting the next one would be 32, so on and so forth, 64. This one would be 4, then 2, then 1, then a half. All right, so as I approach 7 from the right, I'm going to negative infinity. And over here, I'm going to positive infinity. It'll take me a long time. All right, so now let's actually get the inverse of this function. Yeah, I guess I can leave the camera right there. All right, so when you have an isolated x, you can basically say, how would I solve an equation here if I wanted to find out when this thing equaled 23? All right, this will just be our generic x. Our output over here is our input over here. So there's our generic x. All right, so I think I moved to 7. All right, let me get rid of this because I really want to concentrate on just what we're looking at here. So addition of 7 becomes subtraction of 7, multiplication by 8 becomes division by 8, and the inverse of 2 to the is log base 2 of. And I'm going to stop it right there for a minute and let you look at that. And then look at this and tell me if you can make a connection. Boy, the asymptote of this was x equals 7. I wonder where I look. The first differential is 8. Wonder where I look. And how could I get that second differential of 16? And what's the inverse of division by 20? Multiplication by 20. And what is the inverse of subtraction of 2005? Adding 2005. So now my inputs are amounts. And my outputs, took me a while, are years. Over here, years get me amount. Over here, amounts get me years of something. I didn't tell you what kind of amounts. All right, so I see a 7 and then I want 7 plus 8 over here. 15 should get me, well, let's do it. 15 minus 7 is 8. 8 divided by 8 is 1. We have been studying the value of the exponent and put on top of a 2 to get a 1. That's 0. 0 times 20, 0 gets me year 2005. If I switch the x's and the y's, I should have 2005, 15. Yep, I sure do. And 7 plus 16 seems to be an x horizontal distance of 23. 16 to the right of x equals 7 is 23. And let's put 23 in. 23 minus 7, 16 divided by 8 is 2. I might as well erase here at this stage. 2. What do you put on top of the 2 to get a 2? 1. I get a jump of 20. I get a jump of 20. Okay, which takes me to 20, 25. I got a feeling the next one's going to be 32 units to the right. 32 plus 7 is 39. I'm guessing 39 is going to get me another jump of 20. It's going to get me 20, 45. Well, let's put 39 in. Go back to x minus 7 over, what was it? 8. Yes, I can see it here. 39 minus 7, 32. 32 divided by 8, 4. Can we put on top of 2 to get a 4? 2 jumps of 20. I got a feeling that if I want to get 4, I'm going to go down 20. I got a feeling that, what did I say? Down 20 would make this 1985. And it sure looks like I'm 4, 7, I think 11 ought to get me 1985. 11 minus 7 is 4. 4 divided by 8 is a half. Oh yeah, what's the exponent you put on top of 2 to get a half? Minus 1. Going down 20. So there's some nice patterns here, and if you see them, then it's effortless to graph it. All right, let's try another one. I'll pause the video and let's see if you can maybe get, let's see, do I want to do it? Let's just do, yeah, this is practice. So let's go after it. All right, I should be in a classroom, then I could just switch the computer around, but we'll keep it where it is. Let's try this one. Let's try 32. Let's do a decay. Let's do 32, 1/2, because this is going to be a long video otherwise. T minus 2000 over 25 plus 4. Yeah, that should work nicely. All right, so you have a go at it. Pause the video. You try to get the graph of this with the differentials. Do the inverse over here. Get the inverse. And maybe this time I'll write the inverse first, and then we'll do the graph. So we get a slightly different approach here. All right, so I see 32 on top of 4. That's 4, then I'm going up 32 to 36 units. And then I'm going to take half of that. Half of 32, 16 plus 4, I'm going to be at 20. I'm going to look at something like that. All right, so what year gets me 36? Looks like 2000. In the year 2000, I got 36 or something, and then 25 years later, I've got half of that. So 2025, I get 16 and 4, which is 20. And I got too many numbers that look the same, but let's look at the inverse of decay. I think you're looking at decay. All right, do I want to do that right now? Or yeah, that's what you should have gotten. Okay, a logarithm that looks like that. All right, but let's see if we can get that right now by doing the inverse of this. Okay, so what's the inverse of this? Well, I got to pretend I'm solving an equation. So let's pretend that there's some number over here. All right, and I'll call it x over here. Looks like minus 4. Looks like I'm dividing by 32. Looks like I got a logarithm again with a base of 1/2. All right, and therefore I've got my differentials right here right now. Looks like I got x equals 4. Oh yeah, that's the difference. That's the inverse of y equals 4. This is x equals 4. It looks like my first differential is 32. So let's do that. Let's do 32 here. Why am I doing it? Because when we read the x-axis, we read from left to right, smaller to bigger. And on the y-axis, smaller to bigger. Okay, so 32 goes here. And then the next one is half of 32, which is 16. The next one would be 8, 4, 2, 1. I'm getting closer and closer to the number 4, asymptotic behavior. So I've got my graph that looks like that. And I'm going to be going from years to amount over here. So I'm going to go from amounts to years. And I want to get the inverse of multiplying by 32. No, where was I? The inverse of division by 25 is multiplying by 25, and subtraction of 2,000 becomes addition of 2,000. Okay, so 4 and 32 gets me 36 over here. 4 and 16 gets me 20 here. Right, and now I want to make this the number 1. What makes it 1? 36. All right, so that gets me a 0. Times anything is 0, so that gets me 2,000. Yep, and 20 is going to get me 2025. You should throw the 20 in to see how. 20 minus 4 is 16. Yep, 16 over 32 is a half. What do you put on top of a half to get a half? 1 times 25, 25 plus 2,000. All right, so that takes care of exponential growth. We've got exponential decay. Let's do e to the x and ln of x, just to get a sense of the differentials. And in my class, I make sure that everybody knows approximations. E to the negative 1.1 is approximately 1/3. E to the negative 0.7 is approximately a half. E to the 0 is 1. E to the 0.7 is approximately 2. And e to the 1.1 is approximately 3. I don't start teaching the rules of logarithms until we play with that for, several weeks. So I do e to the x a little bit differently, ln of x a little bit differently. And just as an introduction to e to the x and ln of x, and then I'll do some rapid fire 5 assignment for homework. But let's just look at y equals e to the x. E is approximately 2.71. Okay, it's its own derivative, it's its own second derivative, it's its own. When you get to calculus, magical calculation. All right, so let's look at y equals e to the x minus 0 over 1 plus 0 times 1. A lot of those symbols are unnecessary, absolutely unnecessary. Okay, but I can see my differentials now. Can you? Can you see that y equals 0? Can you see that my first jump is 1 unit? My second jump is 2.71. My third jump is 2.71 squared. Okay, that's what e to the x is. It's 2.71 times 2.71 times a little less than tripling. Okay, I've got a function that's a little less than tripling. Certainly more than doubling. Okay, so it looks like this. So what's the inverse of that going to be? Well, the inverse of y equals 0, hope you're answering it for yourself, is x equals 0. The inverse of a vertical of 1 is a horizontal of 1, and then 2.71. And so we have, boom. Not going to do e to the minus x, but e to the minus x comes down in the other direction as a log. All right, so what do we have here? E to the 0 is 1, and e to the 1 is 2.71. Therefore, we're going to do the inverse. which is the ln of x, which is another fancy way of saying this. Okay, so if I put a 1 in here, what do you put on top of 2.7 to get 1? So if we, oh God, what am I doing here? 1 gets me 0. Okay, so you put a 0 on top of that, right? And if I want to get 2.71, what do you put on top of 2.71 to get 2.71? Hope you say 1. That's an x distance, yes, and a y distance of 1. All right, so can we maybe fill in a couple of these other values just to get a feel? I said that e to the 1.1 is 3. All right, so this is e to the 1 is 2.71. Does it seem like 3 be just a little bit bigger than that at 1.1 might get us 3? And over here, does it seem like negative 1.1 gives us the reciprocal of 3, 1/3? Okay, you got to start getting a feel for these numbers, or you're not going to have a feel for this function. And then the inverse of this would be using numbers like the ln of 1/3 is approximately negative 1.1. The ln of a half is approximately negative 0.7. The ln of 1 is exactly 0. The ln of 2 is approximately 0.7. And the ln of 3 is approximately 1.1. I hope you understand why we've been doing so much work with negative exponents now, so that you can follow this discussion. All right, so let me just do a graph of e to the x and then the inverse of it. And I'll try to do the inverse, and it may be interesting because I convert e to the x functions into a standardized triplet. Right? I use e to the 0 and I use e to the 1.1. So let me just do something real quick here. So y equals 5 e to the x minus 3. Now I don't want a 3 because I'm going to use tripling. X minus 4 over 6 plus 7. So how do I graph that? Well, I say y equals 7, and then I make a first jump of 5, and then the next jump 15, which is 3 times that. And the next one would be 45. Provided I make this thing equal 0, and then this thing equal 1.1. If I make it equal 1.1, I'm tripling. All right, so that gives me this function. What makes this 0? 4. So if I put a 4 in, e to the 0 is 1 times 5 is 5 plus 7. 5 plus 7 is 12. And then over here, if I make this thing equal 1.1, it's not hard to do. That's why I picked 1.1. It's an easy multiplication. So that's 6.6 plus 4, 10.6. 10.6 is an approximate 15 plus 7, 22. Okay, so I do a lot of rapid fire 5 graphing e to the x. That video is already made. So if you want practice graphing e to the x and ln of x, just, I guess, type my name on the YouTube channel and look for rapid fire 5 graphing e to the x, graphing ln of x. But what's the inverse of that? Well, the inverse of this function is, let's see, let me write it here. Y equals 5 e to the x minus 4 over 6 plus 7. And this I haven't done with 3 before in this context. So the inverse of that is x minus 7 divided by 5 times e to the becomes, excuse me, e to the becomes ln of, and then multiplication by, let's see, x minus 7 division by 6 becomes multiplication by 6, and was that a 4? Subtraction of 4 becomes addition of 4, and so this is my inverse. How would I graph this? Well, I look at 7. X equals 7. See if I can turn this a little bit that way. God, I hope I'm not losing you here. I'm not going to do this again right now. All right, so x equals 7. Yeah, I think you can see everything. I know the inverse of growth is going to look like that. And so what is my first differential? 5. My next one's gonna be 15, 3 times that, provided I pick the right numbers. What numbers do I want? I want the ln of 1, and I want the ln of 3. And that should bring me right back to what I did over there. So what makes a 1? A 12, right? And the ln of 1 is 0. Times 6 is 0, plus 4 is 4. So therefore 12 gets me 4. Where am I? 12 gets me 4. 7 plus 5, yes, there we go. 12 gets me 4, and then the next one is going to be 6 bigger, I guess, which is going to be 10 without looking. Oh, wait a minute, I want ln of 3. Yeah, I said I might make a mistake here. So I want x minus 7. I want x minus 7 over 5 to become the number 3, because that's 1.1. There we go. So 15 plus 7 is 22, which is actually this number here. Okay, so that's good. So 22, which is 15 plus 7. Should have gotten it that way. I'll get faster as I keep doing this more and more times. So 5 times 3, 15, plus 7, 22 is going to get me ln of 3, which is approximately 1.1. So there's my 6.6 plus 4, 10.6. And that's an approximation. But I got a feel for the calculation, right? And I don't think if all you do is transformations, there's your exponential decay, here's your exponential growth. If we, well, actually, you don't even do transformations for inverses. You do, all kinds of flipping over the X and Y axis. Great. Well, to me, that's a video game. I'm sorry to say that, but I think you have to have a feel for the numbers that you're working. So I don't teach transformations. Try to get a feel for the calculation by plugging numbers in and then shortcutting the process as much as possible. All right, so there's my spiel. And hope that helps.